Okay, in this lesson, we're going to go over we're going to expand on the previous lesson and show the matrix representations of the algebraic way that we were using before to move points through the pipeline by using certain transformations, like scaling it, rotating it, or translating it. We're also going to discuss the homogeneous coordinate system, as well as do a quick example showing both ways in which we could do it, the algebraic way and the matrix way. All right, so let's move to the board. So I have up here already from the previous lesson, this is the algebraic results of scaling something, rotating it, and translating it, how it affects the x and the y of each point that we give it. Okay, and if you don't understand this, go back to the other video and watch that first. Okay, now these are the matrix representations of the same thing. One of the first things you should notice is that these are 3 by 3 matrices, even though we're only affecting 2 components, and that should seem a little odd at first, and it should be. Now, we're going to discuss the homogeneous coordinate system first, and then this will all kind of make sense. So this point, some point xy, we're going to represent as a column vector, like so, xyw. Okay, so this same point is going to have x, y, and w. We're going to add this extra dimension, but I should be clear in stating that this is not to mean an extra dimension in the geometrical sense, right? I don't mean a third dimension. I mean another component. So we have only two. This is a two-dimensional point, right, with an extra component that we're going to use for, well, two main reasons. Okay. We are going to, the first is so that this translation is possible. There is no way to represent a translation of a point in a matrix without having an extra column over here so that you can add something to the existing point or the existing component without somehow scaling it instead. Okay, so this has to be out here. Now, we're going to just arbitrarily say for now that any point, we're always going to make its w component the number 1. Okay, and I'll explain why by showing you the example of how we can get a multiplication of a point by this matrix to get this algebraic result. Okay, if we were to take the point x, y, and this w component of 1, right, and multiply it by this translation matrix, we would get x times 1, okay, plus, this is a 0 times y, plus an a times 1, okay? So our x prime would be equal to x plus a. And look at that, that's what we wanted. And the y prime would be equal to, there's 0 x's, there's 1 y, and there's 1 b. So y plus b. Okay, and the w prime would just be 0 x's, 0 y's, and a single 1 times 1. So the w component doesn't get affected. If we choose 1 for it, then it remains the same, which means every time we do it, it's going to be 1 no matter which one we multiply it by. The second important thing is that this 1 is used here on this a and b, right? Because it's x, 1 times x, 0 times y, and this 1 times a. If this was any other value, we would actually be taking the a and the b that the user chose, and we'd be modifying it first by multiplying it by some scalar value other than 1. So if this was not 1, this translation wouldn't work. It would be like x prime would equal x plus some scalar, factor times a, right? Because a right here, this would be the scalar factor. Okay, we don't want that. We want this to be 1. Okay, and now that that sums up why we need it. Okay, so because we need this extra column to do translations, if we add a 1 here and make this a 3-dimensional vector, even though it's only a 2-dimensional point, then we can go ahead and multiply it by these. And what's great is then with anything else that doesn't really need it, like this rotation and this scale, we're just doing a row here of 0, 0, 1, which basically it guarantees that nothing else actually gets affected by these matrices. So we're using this extra imaginary dimension now so that we can pull off translations. And that's why we have it. Okay. Now, also, let's say we had an axis here. Okay. Let's say we have some vector v. Well, from any, linear algebra would tell you that this is also v, and this would also be v, and so would this would be v, and this, ooh, that was bad. That would be like minus v, so on. So a vector is only defined to be a direction and a magnitude. In the specific definition of a vector, there is no talk or anything about the position. It's because vectors do not have a position. They exist everywhere in the world and nowhere in this at the same time, in a way, because really they're just representing a direction and a magnitude. So you can use it to move a point from here to here by giving it a direction and a magnitude to travel, so how much it's going to travel and in what path. It can be used as like forces. You could say the force is coming from this direction and it has this much force, this magnitude of force, because that's what we use vectors for. Well, homogeneous coordinates allow us to write vectors like vector v to contain its, well, let's not use x and y so we don't confuse it. Let's say an s and a t and a 0. So what we do is we say it's defined with some s magnitude and some t magnitude to show a direction, right? And then we just choose the w component to be 0. If we do that, it should be quite easy to see that if we were to take this vector v, right, and multiply it by a translation matrix, we get s times 1 plus 0 times t plus a times 0, which is 0, right? So s prime ends up equaling s. T prime is t, and w prime is 0, which means v prime is the same as v when we translate it. And that's perfect. That's exactly what we want. That means that a vector, if we translate a vector, if we attempt to, it will not be affected by the translation, because vectors don't translate. They exist wherever they need to be because they don't represent a position, and that makes sense. But vectors can be scaled because we can change the magnitude of the vector, so they are affected by the scale matrix, and they can be rotated, and because obviously you can change the direction. And if you were to multiply that, see, the 0 component only has to do with this little column right here, and this column doesn't have any effect in the scale and the rotation matrix, only in the translation. So it's great. We can use vectors and points, and we can move them through the pipeline using the same matrices, and vectors somehow just no longer get affected by the translations, even though the points do, because we choose points to have a 1 and we choose vectors to have a v. So this is what we do for the homogeneous coordinate system to actually be able to multiply these by matrices and make our calculations easier. Okay. Now the other thing here is I'm choosing what's called column major form because I'm writing my vector as a column and not as a row. We can also choose by convention this. This is perfectly legal. This is called row major. Okay, row major, column major, column up here, row down here. Now you can see, I mean, one of the things you should have probably asked yourself if you didn't know already is, why did I take the point and multiply it on the right hand side of the matrix? Why am I taking a point and multiplying it by some matrix M, and not taking the point and multiplying it by some matrix M like this. Well, if you look at this, all these matrices are 3 by 3, right? So M. And P, right, P is in column major, has 3 rows, right? And it has 1 column, 3 by 1. Well, matrix math tells you that the rules, in order to multiply two matrices together, the inner dimensions have to match. And to put it another way, the columns of matrix A have to match the rows of matrix B. And obviously, if I put P on the other side, I'd have a 3 by 1, and 1 and 3 do not match, so it does not work. But if we were in row major form, right, in row major, we would have, this is a 1 row by 3 column matrix, and then this is good, which means if we're in row major, we multiply our points on the left-hand side, and if we're in column major, we multiply our points on the right-hand side. So what's really important is if you watch some of the earlier pipeline videos, I mentioned that it is very important that when you're doing these transformations that you do them in the proper order, right? You need to make sure you scale it first, then you rotate it, and then you translate it. Or do you scale it, rotate, and translate? So the reason why I wrote them two different ways is because we're going to use the rule of thumb that depending on our convention, right? If for column major, we know that we're going to multiply this by point P. And in row major, we know we're going to multiply this by point P as well. Well, in column major, we know P goes on the right. So we're always just going to say that because it goes on the right, we're going to read from right to left. Our order of operations is from right to left, from where the point starts to what it's multiplied by, which means conversely, when we're in row major, we start from where the point is and we draw a line towards where we're going, so it's left to right, and that's the order of operations. It's pretty simple. Whatever side the point goes on, you draw a line in the direction towards the matrices that it's being multiplied by, and that's the order of operations that's important. Now, for the most part, I'm going to use mostly column major, okay, which means we are going to be using this what seems like a backwards convention, but if in this case, I'm scaling it, I'm rotating it, and then I'm translating it, even though I wrote it TRS, okay, because the point's on the right and we go to the left. All right. But the last thing to note is that the matrices themselves are also in column major format. Okay, so you have to, if I'm transposing this vector or point, all right, in column major to turn it into row major, that's just me transposing it, right? Each column or each row becomes each column of this one. We have to do the same thing with the matrix. Okay, so the translation matrix, for example, in row major, right? This column becomes this row, so 1 0 0. Then we get 0 1 0, and then A B 1 would become the last row, A B 1. So this is the translation matrix in row major. So then we could take x, y, and 1 and multiply it by this, and we would get this result up here, the algebraic result we were looking for. So really important, you have to take a column major version of a matrix and transpose it in order to turn it into row major. And then conversely, the row major, to go into column major, you take a row major matrix and you transpose it to get back to column. So you can transpose back and forth to get back into each convention as much as you want, but you have to make sure that you are on the same convention between the vector or point that you choose to multiply by and the matrices that you're multiplying. All right. So now that we have the matrices here, feel free to actually multiply these out if you want to see them go back into this form. If you don't believe me, do a little playing around with these, multiply them together, and you'll see that they do in fact create the same representation algebraically when you multiply them by a point or a vector. All right, so let's do a problem real quick. So let me clear this out. All right, so this is our problem. We have the point 1, 1, and we want to scale it by 2 on both the x and the y. We want to rotate it by 90 degrees, and we want to translate it 1 unit to the right and do not translate anything in the y-axis. And what's the result? And here's what we should get, -2 and 1. So let's do it the algebraic way first, because it'll help us, and then we'll see how much easier it is with the matrix way. So let's say the point as a result of scaling on the x, right, is equal to that scale x times the original x, which is 2 times 1, which is 2. The result of scaling on the y is simply scale y times y, which is 2 times 1, which is 2. So our point after scaling is 2, 2. Okay. Our point after rotating, our point after rotating on the x here is x cosine theta minus y sine theta, which is equal to x, which is 1, multiplied by the cosine of 90, which is 0, so this term goes away. We get a minus 2 times the sine of 90, which is 1, so we get minus 2. Okay, the point rotated y is x sine theta plus y cosine theta. Well, this term goes away, so we're left with this 2 times the sine of 90, which is 1, which is 2. So after that, we have -2 and 2 after the rotation. Finally, our translation, our point as translated on the x is just equal to x plus t of x, right, which is just equal to -2 plus 1, which is -1. And we know that our point translated with y is just the same thing it was before, because t of y is 0, so we get 2. So our answer, final answer, is -1 and 2. And we had to do it kind of step by step by step, taking the point from the previous calculation and using it in the next one, and we end up getting the right result. So that's the long way, essentially, that we can do it, which is fine. Or we take this point first, and let's rewrite it 1, 1 here in the homogeneous, and I'm going to use column major. So we're going to call point P this 1, 1, 1. Okay. And then we know that because our point P is in column major, that it goes on the right-hand side, which means we're going to go this direction with our order of operations. We're going to scale it first, then we're going to rotate it, then we're going to translate it. Okay. So let's find our matrix M. Right. So M is the result of multiplying the scale, the rotation, and the translation together. Okay. So start with our scale matrix. Our scale matrix is we need 0, 0, just like so. This is our x scale, and this is our y scale. So this is 2 and 2. This is our scale matrix. Okay. Our rotation matrix is going to be, we're rotating by 90 degrees. Well, this is going to be cosine of 90, which is 0, minus sine of 90, which is -1 and 0, and then sine of 90, which is 1, and cosine of 90, which is 0, and then 0, 0, 1, and translate. And here's our A and our B, our T of X and our T of Y, which is 1 and 0. So here's our 3 matrices. And now we're just going to multiply them together. And we do this by, it doesn't matter the order. I could do R times T first. I could do S times R. What I can't do is S times T, right? I mean, as long as they're in the same positions, I can multiply them in any order I want, but I can't just they have to be in the same location. So S and R and T. So I'm just going to go right to left. S times R first, and then that result multiplied by T. Okay, so doing S times R, I'm going to use a quick matrix multiplication trick that I like. Bear with me on the definition. It sounds complicated, but it's not. So the idea is whichever matrix is on the right, okay, we look at the matrix on the left as separate vectors, as vector v1. Let me use a different color. Call you v1. These are the column vectors of the matrix, v2 and v3. So if we look at each one of these columns as their own vector, okay, then the matrix on the right tells you that for this slot, okay, for this vector, this column vector of the matrix on the right, represents a linear combination of the 3 column vectors on the left, where the spots here, the components, represent the coefficients to be multiplied by each one of those column vectors. Okay, so simply put, again, this means take 2 times the first column vector on the left side. Okay, so this would say 2 times v1 plus 0 times v2 plus 0 times v3, right? Sorry, I won't even write that because that'll confuse people. This equals our result, which I'll call v prime of 1. So instead of writing it there, we'll write it here. Okay, v prime of 1. Now v prime of 1, so in our result, this is our resulting matrix R, we get v prime 1, v prime 2, and v prime 3 all just become, again, column vectors of this matrix, and this is how we form the other matrix. Okay, so one more time, each slot here, each column of the result is simply the linear combination of vectors on the left-hand side as column vectors, where the components of the column vector on the right-hand side represent the coefficients with which to multiply the linear combination, which to multiply the vectors. Okay, so that would mean that the result of the first one, right, is 2 times the first vector, and then we're not picking up the second or the third. Well, 2 times v1 is just 0, 2, 0. Okay, so 0, 2, 0 is our first. Our second vector is 2 times the second vector on the left-hand side, so negative 2, 0, 0, because we don't pick up any other ones. And this is just 1 times the third column vector, and we don't take v1 or v2, so 1 times v3 is just 0, 0, 1. So that's our result of that. Now we need to multiply this guy by t. We'll do the same thing. So this is the coefficients, and this side are the column vectors. So this is 2 times the second vector. So our first slot is 0, 0, 2, 0. 2 times the second vector, right? Then we have negative 2 times the first vector, so minus 2, 0, 0, and 1 times the third vector, which is 1, 0, 1. So this is our matrix M. Okay, so I'll clear up some room here. All right, so now that we have our matrix M, you can see how if I, barring all the explaining I did on that, I could have put this matrix together quite quickly compared to all of the algebraic way of doing it. It's really simple to multiply when you think about these scalar multiple ways to do it. So then we just take the point, 1, 1, 1, and we multiply it by matrix M. And we get our result. And that's 0, minus 2, plus 1, which is minus 1. This is 2 plus 0 plus 0, and this is 0 plus 0 plus 1. So our result, P prime, is equal to negative 1, 2, 1, which is a point with the coordinates x equals -1 and y equals 2, which indeed is the right answer. So here we go. There's our matrix multiplication way of doing it. It's nice to see. I mean, you can look at matrix M and really you may not know right away what it's doing, but really this single matrix is the result of scaling something, rotating it, and translating it in that order. And all you have to do is multiply the single point by this matrix, and you get the result of moving this thing from its model space point into the world, where it's scaled by 2, rotated by 90, and moved 1 unit to the right, and that's where it exists in the world. So we're going to do a lot more examples. I'll probably do a video where it's just like 3 or 4 examples of this, and maybe we'll do one in column and one in row major, just so we really get used to maybe not getting so comfortable actually with one over the other and forgetting that there is another convention that we need to use if anyone else does. All right, I'll see you next time.